Firing a single push notification at enterprise scale is the result of a complex, high-volume data operation. To handle millions of these messages daily, the system requires a massive underlying infrastructure that remains stable under heavy load. This system serves as the central alerting mechanism for vital user information. It is responsible for routing billing events, package tracking updates, and time-sensitive promotions. To reach users across different platforms, the pipeline must support 4 mandatory delivery channels: iOS push, Android push, SMS texts, and standard email. The operational constraints are rigid. The pipeline must ingest triggers from dozens of separate internal microservices, process millions of events per day, and operate in soft real-time. Crucially, the internal engineering team does not control the final delivery step. The last mile requires handing data off to unpredictable third-party networks. Designing this system is a challenge in building a reliable internal pipeline that can interface with highly unreliable external vendors. Reaching end-user devices requires integration with specific third-party delivery gateways. For an iOS device, the system must format a specific payload and device token for the Apple Push Notification Service, or APNS. Android devices follow a similar routing path, but through Firebase Cloud Messaging. SMS alerts require a handoff to commercial telecom vendors, while emails are routed through third-party SMTP relays like SendGrid or MailChimp. These 4 distinct vendors operate with entirely different API requirements, latency profiles, and failure modes. Relying on commercial vendor uptime and their specific rate limits represents the primary architectural threat to the internal system. Before an internal service can trigger an alert, the system must independently gather and store routing data from the user. This diagram shows the initial contact gathering flow. When a user installs the application or signs up, their device passes contact information through the load balancer to the API servers, which store it in the database. The schema separates routing data. Emails are in the user table, while hardware tokens set in the device table. A single user ID links to multiple device tokens. Sending a notification requires querying the database to execute a fan-out process, reaching every registered device simultaneously. Data retrieval is a mandatory blocking step for every notification, making read speed a critical performance bottleneck. A common approach is a single monolithic notification server handling every step. This synchronous setup receives an event, queries the database, builds payloads, and holds the connection open while calling Apple or Twilio. This is blocking I/O. The server's threads are frozen waiting for external networks. During a marketing blast, a massive spike in internal requests can hit the server all at once. If the SMS provider experiences an outage, memory overloads as threads wait for a timeout. This failure cascade crashes the server, immediately taking down the email and push channels as well. Synchronous coupling with external providers makes the entire system a single point of failure. It is guaranteed to collapse during traffic spikes. To separate fast internal intake from slow external delivery, we place a fleet of notification API servers behind a load balancer, supported by a cache and database. These servers quickly validate requests, fetch routing data, and bundle the event. We introduce message queues as an asynchronous buffer between intake speeds and external latency, split into specific queues for iOS, Android, SMS, and email. This isolates failures, and SMS queue backup has no effect on the email or push queues. Worker pools handle the final leg of the journey. These workers pull raw events from the queues, format the proprietary JSON payloads, execute the external HTTP calls, and record the results. This decoupled architecture allows workers to scale entirely independently based on queue depth, protecting intake API servers from external latency. Let's trace a payment failed event from an internal billing microservice. As shown on the left of this diagram, the request hits the API servers. They validate the payload and query the cache for the user's phone number and device token. The API server immediately drops the bundled event into separate iOS and SMS message queues. The API server's job is complete, freeing it to handle the next request. Simultaneously, worker pools autonomously pull events from the queues at their own pace. The workers perform final formatting and push the payloads to APNS and the SMS carrier. Internal service speed is no longer dictated by the response times of external APIs like Apple or Twilio. An enterprise-grade notification system functions as a high-capacity asynchronous delivery pipeline. This design allows disposable workers to manage the friction of external networks while keeping the core internal system pristine and responsive. However, this raises new questions. What happens when a worker fails mid-delivery? How do we prevent duplicate messages? We also need to handle user opt-outs, template management, and rate limiting to prevent overwhelming our users. This diagram shows the next stage of the architecture. In Part 2, we will upgrade the system to handle extreme reliability, deduplication, and user preference tracking.